are necessary for you to understand the calculations that we will be doing in the future. Some techniques are only applicable for certain types of quantities. And I have to give you the names of these so that you know when and why we do things, the calculations that we will be doing. Okay, so what is statistics? Well, in elementary statistics, there are really two different branches: descriptive statistics and inferential statistics. The first half of this course will be involving descriptive statistics. It consists of designing experiments, the collection, organization, and summarization and presentation of data. So it's really just, how do you get the data? How do you organize and present the data? Inferential, so that's the first half of the course, chapters 1 through 5. The latter half of the course will involve inferential statistics, which consist of generalizing from samples to populations, performing hypothesis tests, determining relationships between variables, and making predictions about a population from a sample. So this is really the important part of statistics. This is the meat of the course. But in order for us to understand inferential statistics, we use in inferential statistics the techniques of descriptive statistics. So this is really just a reinterpretation of what we've done here. And so it's necessary to first complete different descriptive statistics. So a variable. I will give you several definitions of what a variable is. This is my first attempt. It is a poor attempt, but it's an attempt to give you an intuitive idea, not really a proper definition, merely an intuition. So I'll start with some intuition, and then later on, I'll redefine these, actually more than once, being more and more precise. A variable is a characteristic or attribute that can assume different values, such as height, weight, temperature, number of phone calls. So those are variables. A variable whose values are determined by chance are called random variables. Of course, in reality, no, that's not a random variable, but we'll give a better definition later. Data. Data are observations such as measurements, genders, survey responses that have been collected. Statistics. What is statistics? Statistics is a collection of methods for planning experiments, obtaining, organizing, summarizing, presenting, analyzing, interpreting data, and drawing conclusions based on this data. A population. A population is the complete collection of all elements that you are interested in. So things like scores, peoples, measurements. And so this is just the complete collection of everything that you are interested in studying. And so the collection is complete in the sense that it includes all subjects to be studied. What's a better definition? A population is a set. A census is a collection of data from every member of the population. A sample. This is a sub-collection of members selected from a population. A sample is a subset of the population. So the Gallup Corporation collected data from 1,013 adults in the United States. Results showed that 66% of the respondents worried about identity theft. What is the population? So, what is the population here? We have here, is it Gallup? Is it 1,000? Is it 66%? Is it identity theft? Is it the United States? What is it? What is the population? For this example, what's the population? Let's see if anyone answered in the chat. Hmm, 2013. Okay. So what's the population in this particular situation? And people can just turn on their mics. Try to answer this. So what's the population? What are we interested in studying? So remember, population is the complete collection of what we want to study. So what do we want to study? Let me see. Who do we want to study? So who are we studying? Anyone? Don't be shy. Turn on your mic. Answer. I'm waiting for answers. Who are we interested in?
Population of USA adults.
Yes. Yes. So if you look here, we're interested in the adults in the United States. That's our population. So that's who we're interested in. We're interested in adults in the United States. So not everyone in the United States, just adults. I guess children don't care about identity theft. If you are, 6 months old, you really don't care that someone stole your identity. So quote unquote, we only want to, or whatever. Maybe you don't care, but we don't care. We don't care if an infant has been, the object of identity theft. I'm only interested in an adult in the United States. So what is? Here it is. So what is the population? So the population consists of all, of course, this is probably not current, 241,472,385 adults in the United States. So it's all adults in the United States. What is the sample? Now that's easier.
1013.
Yep. There's the sample. So it's these people are the sample. That's the, so this is the set. And here is the subset. Here, subset. And so there's the subset. And so the sample consists of 1,013 polled adults. What was the objective? So what was the objective of this?
Identity theft worries.
Yes, okay, identity theft. So the objective of collecting the sample data was to study identity theft for adults in the United States. And so we've collected this sample of 1,000 to give us an idea about what does all adults in the United States, what is their worry about identity theft? So we're collecting this sample to tell us something about the population. And so the objective is to use this data as a basis for drawing a conclusion about the whole population. From this 1,000 adults, what can we say about all 241 million adults about how they are worrying about identity theft? And so from this 1,000 people, we will make some inferences about the other 241 million adults. So now the question, which is, well, they didn't ask here, but now the question that should be in your mind, and we will answer, not today, but maybe in 2 weeks. Did they ask enough people? They only asked 1,000 people. And so is 1,000 people enough to make an inference about 200 million people? And the answer will be, yeah, that's about correct. So we will find, a lot of what you will notice is that I've seen so many incorrect arguments where people, especially online, they, say, well, look, how in the world, can they be correct about something? Because they only asked 1,000 people, and they're trying to make some inference about everyone in the United States. And the answer is, well, do a little bit of mathematics, and you see that, around 1,000, 2,000 people is the correct amount to ask about everyone. And it turns out to not really be dependent upon the size. This could be all 6 billion people in the world, or 8 billion, whatever it is. You would still, sample 1,000, 2,000 people to make a inference about all, 7 billion people. Okay. So it turns out that other than for very, very small populations, your sample size is not dependent upon your population size. And so because of that, people are confused. They are incorrect. As a matter of fact, that almost all, except for experts, almost all statements involving probability, mathematics, statistics, people argue, are almost always incorrect. Obviously, unless they've actually taken, a course in statistics. Their arguments are always wrong. Okay, so parameter as opposed to statistic. A parameter, numerical characteristic of a population. So examples of parameters that we'll be countering: population mean, denoted by this Greek letter mu. Population standard deviation, denoted by this Greek letter sigma. Population variance, denoted by this Greek letter sigma squared. Population correlation coefficient, Pearson's product movement correlation coefficient, rho, another Greek letter. The population proportion, P. A statistic, almost the same. A numerical characteristic for a sample. So if you're talking about numerical characteristic of population, parameter. numerical characteristic of a sample, a statistic. So some statistics that we'll be looking at in this course: sample mean, denoted by a bar. Sample standard deviation, S. Sample variance, S squared. Sample correlation coefficient, R. Sample proportion, P with this, well, this little hat. P with a little hat above it. Or caret. So what you should notice here for parameters, Greek letters. So for parameters, there were Greek letters. Whereas for a statistic, they were, well, regular Arabic characters. So there's these regular characters here. So S, R. Oh, and usually notice that the corresponding Greek letter, so population correlation coefficient, rho, the Greek letter for R, the sample correlation coefficient. The population standard deviation, sigma, the sample standard deviation S, corresponding Greek letter of S is sigma. So if it is if it's a parameter, it's a Greek letter. If it is a statistic, it is usually a lowercase letter, or maybe a symbol above a lowercase letter. So symbol, so it's either a lowercase letter or a symbol above a lowercase letter. Except when it's not. So except for the exceptions. So this is the exception. I think this might be the only exception in the book. So except for this guy, where it's for population, but it's not Greek. Sometimes people use the letter pi for this, but the book doesn't. And actually, most books don't. So I use P.
Can we safely say that statistics is the scaling, parameters is the scaling of statistics?
Well, it's a parameter talks about population.
It's like scaling, projecting the information from statistics up to the population, right?
No, inferring. What you mean is the word inferring. It infers. So it infers from your statistic a parameter. And so we'll be using the statistics to make inferences about a parameter. And the answer is yes. So yes, if you use the word infer. So we're inferring things. So we'll be doing inferences from samples to parameters, from statistics to parameters. Yes. And that's really the main half of the course. So that's like a good portion of the latter part of the course. And the answer is yes. Okay. Okay, then. So that really finishes off section 1.2. Let me go on.